And then another thing, so I'll also send out a Piazza post about this, but I'm scheduling my office hours for 5 to 6 p.m. on Mondays. So it'll start this Monday. And I encourage all of you to attend, even if you don't have questions, just to, come meet me, talk. Yeah.
The other thing is that lab, there's also a lab scheduled in the schedule, but that's not, but we're not going to use it. Effectively, the lab component of this class is composed out of programming assignments that will be in with your homework. So you do it basically in your own time. There's no schedule lab time for that. And then the 2 wet labs that we're going to have, because I mean, we can only do 2 or 3 people at a time, and it's serial, so we can't do that at a regular time. So what we're going to do is when we're going to start having those labs, we'll just have signups throughout the weeks, and some people will do the labs earlier than some other people. We'll try to give enough options such that everybody could attend those, if that makes sense. Any questions? Yeah, for those putting in the cameras, I appreciate that. That helps me look at your faces. So thank you. All right, so let's start. Just to recap what we went last time. Last time, again, this is the introduction. The idea is to tell you a little bit about medical imaging, kind of give you a 10,000-foot view of what is MRI and how kind of it works, but not really dive into all the details. And so I'm gonna wave my hands a little bit like that. Can you see me wave my hands? So I'm gonna do a lot of hand waving. But the idea is to give you kind of also things to look at when we go and dive more deeply. So you'll have slightly hand wavy, bigger picture, and then you understand the details within those contexts. So that's kind of what we'll try to do. And I'll try to give you as much examples and illustrations such that make it easier to go through. Let's see if I'm missing something before that. And I'm going to also try to give you kind of motivations, or also look at and what differs in MR imaging with respect to other forms of imaging. So that's today. And next week we're going to start something. Going to start again, I guess. All right. I talked about anatomy versus function. That's where we ended up last time.
In this house, we obey the laws of thermodynamics.
And there's a difference between the two. So with anatomy, we look at structure, like just anatomical structure, what is there and what isn't. But we don't look at how it works and how well it works, or quantifying how it works. So this is the difference. For example, and MRI is used both for structural imaging as well as functional imaging. And functional imaging, not just brain functional imaging, but you could also cardiac functional imaging, renal functional imaging, lung functional imaging. So you can look at many areas in the body that you can look at function using MRI. The anatomy part is more, I guess, straightforward to understand because, it is or it isn't. But even an anatomical point of view, I told you, but we can look at diffusion. So look at these type of structure that are weighted by diffusion, so it gives you information on how water diffuses through the body, and that can give you a lot of information, for example, on brain connectivity. Any questions up to here? Questions about last time, questions about the class, questions about what we want to do and what we're going to do.
Professor? So this is Maruf. I have a question about the wet labs. So what are we going to do in the wet labs? If you want to answer that now.
Yeah, so it's going to be two labs. One is going to be on a 1 Tesla permanent magnet system, which is a wrist MRI system that's in Corey 187. And there you're going to learn kind of basic of NMR, you know, a little bit pulse sequences, you know, actually you look at the calibration, what the scanner does before you get a scan, how you calibrate things. So you go all through that, and then you write actually what's called a pulse sequence, which I haven't even got into what it means. You'll write that for that scanner using it has a really nice MATLAB programming environment that you can program that scanner. The other lab is going to be on a 3 Tesla clinical scanner at the brain imaging center. And there we're going to more focus on imaging part, like the imaging part. And a lot of the things that I'm kind of showing in class, we're going to derive artifacts and, you know, what would look like. I'll show you some examples. There you're going to actually perform scans and see those in real time by changing, you know, parameters and see how they affect the images. Does that make sense?
Yeah, it does.
Anyone else? All right, let's dive in. So here's some examples of this is functional cardiac imaging. And with MRI, you could do, for example, real-time color flow. So you can make MRI sensitive to flow, which is pretty amazing, I think. You know, spins, I mean, I told you, well, I guess after I told you it's sensitive to diffusion, I mean, obviously should be maybe also sensitive to flow. Flow is very different than diffusion. Diffusion is kind of a random process, but flow has a direction and it has velocity and it's more coherent. It is possible to make the signal sensitive to flow. This is example on the left is a real-time acquisition. So you get flow through this, like the measurements of flow through the slice, and with the imaging slice, this is a heart. Blue, I think, is towards me, and then red is the other direction. Or you can do what's called 4D flow. This is an acquisition that's done over maybe 6 or 7 minutes while collecting data and assuming that the cardiac cycle is periodic. And what you could see here is imaging flow basically both in space, in 3D space, and along the cardiac cycle. And this is an example of the pediatric patient. And you can kind of see, this is again the heart. And just pay attention to this area here. This is where the valve is. And you can kind of see that when the heart, not contracts, but extracts, I guess, back, you're not supposed to see blood getting through this valve, but you actually see that this valve has a leakage over here. And you can only really see that in the flow image. It's very hard to see that with any magnitude image. Okay, so structurally, you won't be able to see it. So this has to be surgically repaired, for example. So congenital heart disease. MRI is sensitive to blood oxygenation. So changes in blood oxygenation will also modulate the signal that you get from MRI. And the reason is that hemoglobin and deoxyhemoglobin, the one, you know, whether you have oxygen in the hemoglobin or you have CO2 attached, they'll have different magnetic properties. And so they'll change the local signal in certain areas. And turns out that if you have brain activity, areas that have higher brain activity, neurons will fire more, and then they'll need more oxygen and more sugar and more blood in this area in order to work. And so can you, I'm just gonna hold on 1 second. Yeah. Apologize for that. All right, sorry about that interruption. Can you hear me back? Am I back?
Yeah.
Yeah. Okay, so basically the brain regulates the blood that gets into the amount of blood that gets into the tissue and out of the tissue. And for the amount of oxygen is also being regulated and correspond to brain activity, which is pretty amazing. So what you do then is you induce some the typical experiments that you would do is that you would have some, let's say, visual stimulus to the subject while they're being scanned in an MRI, and then you collect a time series of images, and then you would look at one voxel and you would see, for example, that there is some modulation of the signal over time corresponding to the stimulus. And then if you look at correlation with the stimulus, you can say, oh, this area is more active, this area is less active. So that can tell you a lot about brain activity. Now you can take that even further and do other type of experiments like what's called retinopathy, something like that, where you map the retina. Basically, your retina is mapped into the brain. So your retina is connected through neurons all the way to your primary visual cortex. And then for every neuron location in space that, is seeing, the image that you're looking at, you have an area that processes it in the primary visual cortex. And so what you could do is you can apply this type of a stimulus, for example, these annual rings that kind of slowly grow. And if you have, for example, let's say where my mouse is a neuron that now is not picking the image. Once the annual ring gets to this neuron, then it's being activated, and now it's going to show some signal changes in the MRI at the back of the head, and now it doesn't show it anymore, right? And so you're going to go and do this experiments over and over again. And basically, different neurons that are radially away from each other, so one in the center or one far away, will have a different phase to that response, to that oscillatory response. And based on this phase, you can basically map your retina onto the back of the brain, and that will give you the radial mapping. And if you want to also get angular mapping, you can do a wedge that kind of rotates around, and then from that get the angular mapping, and then map the entire retina onto your visual cortex and understand kind of where things are connected to, which is mind-blowing, right? Just that ability. Now, other people have taken this even further and saying, you know what if we, and this is a work maybe 10 years old, so this has improved since then, still mind-blowing to me. This is from Jack Gallen lab here at UC Berkeley. And what they did is they have shown video clips to people, and then they recorded the response of the visual cortex to those videos. And they tried to create, to regress, find a model, a nonlinear model that can map a clip to the response, and then go back from a response and try to find a clip. And so now what they've done after they do all this training, they go and present a new movie, a new clip, and then they record from the visual cortex. And so, and then the idea there is they want to try to reconstruct what the person is actually looking at by recording its connectivity using fMRI. And the way they've done it, and there's probably other ways today with modern neural networks and all sorts of stuff, but the way they've done it is they go like, they present this movie and they try to find in the database the clips that produces the closest match in response to that the clip is doing. And then they take the best, 16 ones, and they average them. And then they present the average. And so I'm going to show you this video. This is the clipping shown. These are the best matches. And this is the average of them. And you can kind of see how the clips being shown is actually similar to the average, right? So you can almost kind of figure out what this person is looking at, right? Like definitely when there's a person going on, it's here. Like now, you know, oh, it's showing a person. You can kind of see where the center is. There's a plane, so there's a big line. So it's pretty amazing. And today you can do much more than that. This is again work from 10 years old, over 10 years old. So again, this is like processing of process. Now think about what is being done here, right? Like you're trying to figure out how a person is thinking, like what the person is actually looking at. So what's going on, like what they're thinking, like how their brain is actually working. You're doing that through modulation. You know, neurons are firing there, and then there's modulation of blood oxygenation. Then you've got like this nuclear magnetic resonance that's sensitive to magnet, you know, it's like you're looking at basically nuclear spins, like you know, like the tiniest in the universe. You know, it's the nucleus of it's protons. Like that's the tiniest thing that you could, I mean, pretty much you can think of. And then you're interacting with these and receiving signal from them and trying and making, you know, figure out what the person is thinking of. I mean, it's just like I cannot even imagine that this is even possible. And if you told me that, if you told anybody this, maybe 30 years ago, they'll just laugh their hearts out. You know, that is even true. But yeah, things are happening. Other functional imaging, this is spectroscopic imaging. And in this case, it's actually imaging other nuclei, not hydrogen, but actually carbon-13. And this is a experiment that it's been done in a mouse model where the mouse has a tumor. And what they do is they inject carbon-13 tagged molecules, which is pyruvate. Pyruvate is a metabolite. They inject it into the body, and then that goes through metabolism and changes into lactate, and then changes into alanine. So it has a derivative through the Krebs cycle inside the cells. But as it turns out, the metabolism of tumors or of cancer is very different than the metabolism of the rest of the body. And what you can see here is that while you inject pyruvate, there's a lot of lactate being generated in the tumor as opposed to somewhere else. So that allows you to observe metabolism in real time. There's a lot of technology that goes behind that of how to even get signals from carbon-13 because, you know, and so on and so forth, but we'll talk about more about that as we go. But that's another thing that you can do with MRI, actually image metabolism. And this is similar to PET, for example. And PET, right, like you can see tracers going to different places, but now we can see conversion. Like you can actually say that pyruvate was converted into lactate, or the pyruvate was converted into alanine, or, you know, and so on and so forth, which is, again, mind-blowing. Yeah, did you know that MR images are actually complex valued? For real. For real, they're complex valued. I mean, what does that even mean? What does it even mean to have a complex valued image? And why the heck would you have at all? I mean, it's when you take a picture with a camera, there's no phase. I mean, just like there's color, right? But here there's magnitude and there's actually phase. Sometimes the phase is informative, actually has information about structure, and sometimes it isn't. And yeah, knowing how it, when and how, and like sensitizing, for example, the signal to phase is some of the art that you'll learn in MR. There's actually a few things I want to point out here too. This is the brain. Anybody has an idea what this bulge here is? See this small thing here?
Nose.
Who said that? Who said nose?
I did. Allison.
Who's I? Who's I?
Allison. Is the mic on?
Allison.
I don't have mic on. Is it on?
Yeah, no, I can hear it. It takes time to see the people that are actually speaking. All right, yeah, no, it is the nose, but why is the nose in the back of the head? Nose supposed to be in the front, but it's in the back.
Aliasing?
Yeah, it is wrapping. So actually has to do with the Nyquist sampling criteria and all sorts of stuff that actually leads to the nose leaking into the other side. Now it leaks over black stuff, so it doesn't matter. So I was a pretty good technician that prescribed this, so it's not a big deal. By the way, so this, the nose here went outside of the image, so it actually pops up from the other side. But this part also pops out outside of the image, but it actually doesn't show it from this side. So there's a good reason why this happens, and we're going to talk about that. So there's aliasing in some direction they don't. Fun stuff. Now this is a phase image. And so I'm showing the picture, the phase is pixel intensity. But can you tell me what is all this stuff? What is it? Why is it so weird?
Noise.
I mean, why is it not here? I mean, why is the noise so high here, but it's not high here?
I'm gonna just guess, is it because the like the air, it's basically air is what you're seeing, or pockets where there isn't anything, and then there's just, it's coming back with multiple phase information from there because it's not really hitting anything.
Yeah, but why the phase kind of looks so bad over here? But here noise is kind of like, it's very dark, look, there's nothing. It's probably noise there, but it's kind of small. But here the noise in the phase is so large.
There's just more, the values there differ. There's more contrasting values in the phase, whereas the noise on the left agrees. It's just nothing.
So let me just show you this one thing. Let's say graph, right? And I'm trying to here, let's say this is the real part and this is the imaginary. And let's say now I have a vector. And this is my vector. If the vector has a large magnitude and I'm adding noise to it, the noise would cause like an ellipsoid, right? Of variation around the, that will perturb with some, let me change color. The vector would perturb with some, I don't know, ellipsoid around that, right? If I add, let's say, random Gaussian complex noise, right? How's that going to affect the phase? Well, the phase is only the noise in this direction, right? It's the tangent, right? The phase is going to be affected just by the tangent component. Now, if I have now a small magnitude, like I have actually outside of the object, let's say put this one here, and then I add random noise to it, you could see very large variation in phase, because the magnitude is small. The variation in phase is going to be significant. And if there's actually just noise and no signal whatsoever, that means that we're just in the center. And so basically any small perturbation can produce a significant phase change because phase is really not defined for magnitude 0. Does that make sense? That's why when you do phase images, you often see this like really noise outside, and often people just weight it by the magnitude to remove this because it's very hard to see stuff sometimes. Well, phase, I mean, like who would even thought about phase as being something, right? Well, it is in MR. Actually, MRI is all about phase. All about phase. Who does here optics, computational imaging? Anybody? Anybody from Laura's group?
I am, yeah.
Yeah, phase imaging, it's all about that. Like this is just for you. All right. Now phase can be very interesting because this is these are two images, and this is a breast, so it's a cross section through a breast, and those two images look very different. Now, the the image on the left have been taken. So it turns out that fat and water has a slightly different properties in MRI. They resonate at a different frequency. And this image here was acquired such that the water and fat have exactly the same phase. So their signal adds coherently to each other. And so this is how it looks like. This image on the right was acquired such that fat and water have exactly the opposite phase. And so, I mean, if you have tissue that is just water or just fat, you shouldn't see a lot of difference. Like the difference would be in the phase, but nothing in the magnitude. But in the interfaces between the tissue, you'll have voxels that contain both fat and water. And because their phase is opposite, their signal would actually cancel. And so what you see is that at the tissue interfaces, you would see these nulls between fat and water. Isn't that awesome? So that allows you to distinguish, let's say, between a fatty tumor and a non-fatty tumor. Like if you see something and you see, oh, it's hyperintense. Well, how do you know if it's like a cancerous tissue or a fatty tissue? What you do is you put it, you put fat and water opposite phase, and if you see a null, like or some, something like this, a contour around that tumor, that means that it's fatty. Now, here water and fat are added. Here they're subtracted. Any idea what you can use it for? What if I want to create a water-only image and a fat-only image? Can I do that with these two images? What if I take those two images and I add them together? What would I get? Fat here is positive, fat here is negative. Water here is positive, water here is positive. If I subtract the two images, I will get fat. If I add the two images, if I add the two images, I will get water. Does that make sense? Yes?
Can you repeat
Well,
that?
it's kind of true. I said, okay, so fat here in this image is positive and water is positive. Here on the right, fat is negative and water is positive. So if I take this image and subtract this image, I subtracted the water because they have exactly the same sign. But fat here is positive and here is negative. When you subtract, they just add, right? So I end up with a fat image. And then if I add those two images together, the fat will cancel because it has opposite phase. Does that make sense? So I can do fat water separation. And that's a very common thing to do. Now, it's kind of true, but there's also subtleties to what I've just said. So ideally, it's enough to get two images, but sometimes you need three, a third one. But I'm just a hint for the future. Because everything in MRI is slightly more difficult what you anticipate. It is possible to do stuff, but there's always this like complication. So often you need three images for some reason. Very powerful though. Now, other things that phase causes, sometimes phase can cause signal to pretty much disappear. If you have a lot of phase variation within a single pixel, then you might get cancellation of the signal completely, because the signal within a pixel can be positive, negative, J, minus J, and all that stuff, and can add together to zero. So the right image is called a spin echo image. You don't know what a spin echo image, but it's very insensitive to these phase variations. And on the left is what's called a gradient echo. You learn what a gradient echo means. I'm just throwing out those words. The left one is more sensitive to these cancellations. And there's a few things I want to show to you. First of all, do you see the difference between those two images? I mean, there's definitely some contrast difference, but there's also a striking, signal differences. Let me point out some areas. Look at this area and look at this area. Right, the left one, like a lot of it is almost gone, like disappeared, like something is eating your brain. Another area is this one, where here it's not a problem, right? But some worm on the left ate the brain signal, and some worm here also ate the brain signal. Oh, well, if you're an MRI scientist, you would immediately say, oh, this is because it's close to air tissue interface. Air tissue interface causes magnetic field variation, and that can cause this phase problem and loss of signal. Now, where's the air tissue interface? Well, here are the sinuses, what you have here, there's a lot of air tissue, and so that can cause all those, signal losses. And over here, do you know what's here? What? What, Anita? What? What?
Yeah.
What? The ears. Yeah, the ears. The ears are there. So the ear canal is air. And so air tissue interface that can cause these signal losses. All right. So sometimes phase would actually cause a signal loss completely. Not always can be recovered, like in this case, but you have to be aware of that. Any questions?
Yeah, in these images, the signal loss, is it different from being caused by destructive interference? Or is it?
It is a destructive. It is a destructive interference, but not between just two two sorts of tissues. It's a destructive interference because you have a field inhomogeneity in a single voxel that's so strong that has a lot of phase within a single voxel.
Okay.
So you have a distribution of phases within one voxel, and that could cause the signal to be lost.
So is it more in regard to like a sampling issue?
No, it has to do with we'll get to that. You know what?
Yeah,
The reason the physical reason for it is because the field is not homogeneous, and the way that we image here makes it more sensitive to that inhomogeneity.
Okay.
Whereas on the right-hand side, we're able to do something that is less sensitive to this inhomogeneity.
Thank you.
Yeah, no, good question. Here's another thing as a result of phase, but this is called chemical shift. I mentioned that fat and water have slightly different properties. They actually have different resonance frequencies, so they have slightly different frequency that they emit. And because MRI actually relies on, you'll see in a second, it relies on decoding a position of a signal based on its frequency. If the frequency of fat is different than water, you might get something that's called chemical shift. And I don't know, it's very subtle here. Can you see the difference in these three images? Take a look at the skull. There's this white thing around the skull. Can you take a look at that? And then look at those three images and see what's going on there, like how different. Look at the left one and look at the right one and see that there's going to be a big difference. In particular, for example, take a look at this area.
Is it shifted slightly to the right?
Yeah, fat in the left image is actually shifting right so much that it actually overlaps with the brain. It's not anatomical. Like there's no such thing. There's no fat in the brain, right? This is subcutaneous fat. It's the fat underneath the skin. But how come it's showing on top of the brain? That is because fat has slightly different resonance frequency, and the acquisition here was such that you are more sensitive to that effect. And so you could see fat being shifted. Whereas if you do something different, slightly different, you might not be as sensitive. And in this image, you're very little sensitive to that effect. But fat, it can be a real issue. Definitely if you do functional. Who does here functional MRI? Anybody here that does neuroscience and functional MRI? Yeah. So in functional MRI, fat is such a big issue. It could shift so much that it could end up in the middle of the brain. In the middle of the brain, it can end up like shifted by, I don't know, like 10 centimeters sometimes. You know, so you have to do stuff in order to mitigate with that. And you, by the end of the class, you definitely understand all those notions, why this happens, where it happens, how to mitigate, how to make the shift instead of going right to go left, or maybe to go up or down. You know, you can do all sorts of stuff like that, or maybe disappear completely.
Is there any purpose to the image on the left? Can that be used for something else? Or is it more just you're kind of honing in on what you want, and then the right one is what you would finish with?
There's difference. I mean, the left image actually has more SNR than the right image, typically. So it's a phenomenon that you need to be aware of, and there's trade-offs. Like it's actually, you know, a typical answer that I would say here, it depends. It depends on what you're interested. If here it doesn't matter so much, and you gain, you know, from the fact that you're still sensitive to chemical shift, but it doesn't overlap with, you know, regions that you're interested in, so it's not a big issue. And you might gain some other things from that, but sometimes it is a problem. Yeah, fat is not a huge problem in the brain, but it's a huge problem in the body. Imagine if you do an abdominal scan, and now all your fat inside the abdomen, you know, cover around the kidneys and all that stuff shifts. You know, I mean, yeah, that's not, you know, that's the problem, right? It will overlap with organs that you're interested in, you know, could be a real issue. Chemical shift, yeah, sweet. Now artifacts in MRI, most of them can be described using Fourier theory, which is pretty amazing. I mean, you could actually predict how an artifact would look like. And by changing the acquisition, you can exhibit different artifacts for exactly the same phenomena. So on the left here, I'm just showing you some example, is a breast image. And what the heck is going on here? This breast image was acquired over a few minutes. But what's going on here? Do you know?
Is it because the patient's breathing?
That's a good guess, but not in this case. The breathing is less of an issue in this case because they're actually lying, you know, on their stomach, and so the breathing really affects the other side. The breast is not moving.
Is there some kind of interference from like the table or something, like what they're actually on?
Okay, even for men, right, not just women, there is something behind the breast.
Heartbeat?
Now put your hand here and just tell me, what do you feel?
Is the heartbeat.
Yeah, it's a heartbeat. Heart moves. Heart moves all the time, you know, 60, 80 times a minute, you know? And this is a 3 minute acquisition. During that time, the heart's moving. The rest of the tissue is static, but the heart is moving. And so all this crap over here is basically the heart creating artifacts, but those are restricted only to this direction. They're not actually moving into this direction. The artifacts are going only in this direction. Now, if I did the acquisition in a different way, actually those artifacts will go over my the breast, which is a problem. But I can actually think about how I can design the acquisition such that the artifacts don't go in the direction that I'm interested in. Does that make sense? And you'll understand more of that, again, as we go through the class. You understand to analyze this, you understand like, why is that? Okay, I'm just giving you kind of like nibbles, you know, of good stuff of like you know, of why it's worth actually learning about MR, because you can mitigate with all this crap. Now here's another case of breathing and actually non-rigid motion. The patient just moved. This is abdominal scan, and like you can see here ghosting, and you could definitely see blurring. You know, lots of blurring that's happening. What's going on here? This is abdominal scan. This is the spine. This is the aorta. This is an artifact. This is an artifact. This is an artifact. This is an artifact. This is an artifact.
It looks like side lobes, but
Yeah,
I
it
don't know how
does,
that
doesn't
would,
it?
I don't know how it would make them.
Right, crazy, right? Why? It's like replicas, right, of the aorta. The aorta is being replicated. Isn't that crazy?
Is it Doppler shift from the blood moving?
It has to do something with the blood moving, absolutely. Because while you collect the data, while we collect the data, the aorta, the blood is being either going into the slice or not going into the slice. Moving into new blood, fresh blood is coming into the slice, is not coming. So it modulates the signal in a periodic way. Now, if you have multiplication with a periodic function, what is its Fourier transform? Convolution with the Fourier transform of that periodic function, right? So you'll see that this would end up creating a replica of the aorta, because the aorta is pulsing in a very periodic way. The way we collect the data creates certain modulation, and then you can actually do the analysis when we go over this, and you can actually say, oh yeah, this is the replica, and from that replica I can actually tell you exactly what's the heart rate, because if the heart rate was very fast, these replicas were further apart. If the heart rate was lower, they're closer to each other. Pretty amazing. Oh,
So
I know you're all blown away. I know. I'll give you the moment.
why don't you see those for like all, well, I guess like I would imagine there are many arteries and stuff flowing up and down your body.
Yeah, you see them to some extent, but aorta, man, that thing.
It's just a big one. Okay.
I mean, this is like a few meters a second. I mean, this is high pressure stuff, you know. Let me tell you how MRI works, and I have 35 minutes. Okay, crash course in MRI. By the end, hopefully, you know a little bit about how MRI works, or get some picture. So all has to do with three things. So it's all interaction with several magnetic fields within the MRI scanner. There's this thing called magnetic polarization that is generated by having a very, very strong uniform magnet. Okay, so this is the big magnet that needs that. There's a thing called excitation. We're going to excite the spin somehow. And for that, we're going to apply, again, and there's another magnetic field. This time is an electromagnetic field in the RF frequencies. And for that, we'll have actually a very powerful RF transmitter, actually 40 kilowatts or so, that is going to generate a significant amount of radio frequency power that's going to interact with the spins within the body. And then there's the acquisition part, where for this, we encode the position of, basically we use it to encode the position using an extra set of electromagnets, in this case, electromagnets that have a non-uniform distribution in space. And we switch them very fast, but at the audio frequency range. So 5 kilohertz up to something like this, but not more than that. Okay. Lots of current goes into those gradients. We're talking about hundreds of amps. So very powerful audio amps are used for that. Okay, what's polarization? Well, protons in your body, you have a lot of, basically protons, that's, what a hydrogen nuclei is built of, has a magnetic moment. What does it mean as a magnetic moment? Well, you can think of it as a small magnet. Okay, it's an inherent property. It's not effectively a magnet, but it's an inherent property, quantum mechanical property, but we can model this as a small magnet. Protons also have a property which is called a spin, which is an inherent angular momentum. Probably it's not spinning around itself, but we can model it as if it was spinning around itself, because and so effectively you can think of those protons as small rotating magnets. Okay, small rotating magnets. That's what they are. Cute, 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 small rotating magnets. All right, body has lots of protons. But you know what? They don't have any preferential direction. I mean, they could orient anywhere and they tumble through to random energy fluctuations. So they just are randomly oriented and they don't have any net contribution. But once you put those spins inside a very strong magnetic field, what you'll see is that they're actually going to align along that field. Think of magnets. What would happen if you hold actually a compass, right? What would happen to a compass? It would align with the Earth magnetic field, right? There's a tendency, there's a force drawing to that direction, and they will basically polarize. But from an energy point of view, there's a slightly preferential direction. So they're going to align, more spins are going to align towards the magnetic field than they're going to align against the magnetic field from an energy consideration. And what you can think then is that now look at an ensemble of spins, like a lot of spins together, not just a single one. And then this ensemble, we can say, oh, you know what, that ensemble together, because it has a preferential orientation towards the magnetic field direction, then it has actually some net magnetization. So when we do all this analysis in MRI, we don't deal with individual spins, but we deal with an ensemble of spins that allows us to do classical description of MRI. So classical physics as opposed to quantum mechanical physics. Okay, so now you can think of all those spins that are aligned as, one bigger, still small magnet that's now pointing in that direction. Okay. Now this is a magnet. That's the that would be the magnet, and the magnet often it's a solenoid with a superconducting coil that produces a very strong magnetic field inside the magnet. It's extremely uniform, up to 1 part per million over a very large field of view, and it's also very, very strong. And this direction is called B0. That's the direction of the magnetic field. Also sometimes referred to the Z direction for some reason. Now, what's the size of that field? Well, the field, it depends on different scanners, but it goes all the way from, clinical scanners go all the way from 1.5 Tesla. 1 Tesla, so that would correspond to about 15,000 Gauss, 1.5 Tesla. Just to illustrate how much it is, Earth field is 0.5 Gauss. So 1.5 Tesla is quite a lot more than that. So it's a very, very strong magnetic field. The scanner that we have at Li Ka-shing is 3 Tesla. We also have a 7 Tesla scanner in the Li Ka-shing building as well. So there's quite a strong field there. Now you don't have to have a 3 Tesla or 7 Tesla in order to do an MRI. Like for example, we have a wrist scanner which is 1 Tesla. There's also another company that just came up pretty recently with it's called hyperfine research, with a mean that I think it's 65 millitesla. Okay, the field is that it uses, but because it's a very, very low field, it's very low cost, and it's actually portable. So you can move it into the ICU, no problem. And the images are not as good, and but for some things, this could actually make a big difference. So pretty cool stuff. These magnets are dangerous. Here's an example. That's a magnetic oxygen bottle. But if you put it very close to the bore, then this could actually happen. Pretty nasty, huh? Can you hear it? Oh, you're not able to hear it?
No.
Oh. Hold on. Sorry about that. Let me share again. Can you hear now?
Yeah.
You definitely don't want your head inside. And a lot of accidents have happened. So safety in MRI are very important. MRI is also not pretty, it's pretty expensive. So it takes about $1 million per Tesla, kind of a rough number, to site the scanner, just to put it in a room. The cost of renovating the room, creating a shield, RF shield, and all that stuff is between $500,000 to $1 million. Maintaining that machine, a service contract is about $100,000 a year. And so if you want to then go and operate right now, let's say operate, you'll have to pay $650 an hour at Berkeley to be able to scan for research. So think about the 3-4 hours that you're going to get doing the each one of you are going to get practicing, doing the labs, definitely worth the money, huh? It's like a semester tuition. No, I'm just kidding, probably less. But it doesn't have ionizing radiation. This is the inside of an MRI. You have a lot of hardware that's inside. There's the main, this is the body coil that creates the magnetic field. There's also the electromagnets that I mentioned, and there's a few electromagnets. There's one that creates field variation in X direction, one in Y direction, and one in the Z direction. So 3 of them at least. And then also you have a radio frequency transmitter and receiver to here. So all of these need to fit within this tight bore, right? So it's not easy to put them all together, and they need to minimize interaction between them. This is our scanner when it was installed without the covers. So there's lots of, see how many cables going in? I mean, it's crazy. Look, this is just in the table, like how many cables here. So all sorts of receivers and all that kind of stuff. And look at all these cables, cryostats, signals, peripherals, coolers, RF, gradient power, all sorts of stuff going into here. And that's from the other side too. Yeah, pretty fancy machine. And this is Dwight again next to our scanner. Okay, let's talk about polarization. So I mentioned that once you put those spins in a strong magnetic field, they polarize, they align, and now we treat an ensemble of them. They go back and forth from each other, but there's always a net magnetization that's pointing in the direction of the main magnetic field. So we're just going to deal now with the magnetization vector. And when it polarizes, if this is the B0 direction, then the magnetization vector is oriented along this B0. Okay. Now, this is what happens if I somehow am able to tip this magnetization away from the main field through some excitation. What would happen is you'll start getting precession. This magnetization is going to start rolling. Now, this is very different. This is very different than a compass, right? A compass, if let's say I mix the compass, and let's say it's oriented in one way, and now I point it into I'm pointing it I'm pointing the compass. What would happen is that the needle would then point and orient towards the the earth field, but it's not going to precess. It's not going to do all sorts of stuff. What is this precession? Why is this precessing as opposed to going back up? Well, the physics from it is very similar to this case. This Earth is trying to pull, the gravitational field is trying to pull this wheel down, right? But the wheel is rotating, and because it's rotating, it's just precessing around. If the wheel was rotating faster, it was also precessing faster. If the wheel was rotating the other way, then it would precess the other way. In the case of the magnetization, well, the magnetization wants to go up, but it also has a spin, has a spin, and because of that spin and conservation of momentum, it will start precessing as opposed to just going back up. All right. Now the frequency that's going to precess is proportional to the field. So if also in this case of the wheel, if the gravitational field was stronger, things, the wheel would precess also faster. So the frequency is proportional to the field. Increase the field, the frequency is going to increase. And it's generally given by the term gamma times B0. B0 is the field strength, and gamma is some constant. And gamma for protons is 42.576 megahertz per Tesla. That means that if you put a proton spin inside a 1 Tesla field and you tip it, it will produce a 42.576 megahertz signal. At 3 Tesla, it will be around 127 megahertz because it's 3 times that. Does that make sense? Yes? Somebody asked, electrons have spins. Can you compare contrast to ESR, electron spin resonance? Yes, I can. The spin of electron, the gyromagnetic ratio for electron is way larger. And so, the frequencies are usually much higher. It's very hard to get a single electron. Usually electrons come in pair, and that's the problem. But protons, they can actually come by themselves. And so it's much easier to do NMR, nuclear magnetic resonance, the ESR, just because of those frequencies and the fact that you need an unpaired electron in order to do this, but the phenomena is similar. Okay, so once you have this magnetization is spinning, right? You have magnetization and spinning. What happens if I put a coil here? I put a loop, and you have a magnet now that's rotating. A magnet's rotating, you have a loop. There's a magnetic flux that goes through that loop, and that magnetic flux is going to change over time because this magnetization is rotating. So that is going to produce an EMF inside this loop. And that EMF is actually the MRI signal that we're going to pick up. Okay? And we're going to pick it up through this inductive coupling, right? We have some loop, you have some magnetization that's rotating, and that will produce some EMF inside inside that, and that will pick up. That's the signal. Now, obviously, the amount of flux that changes throughout this loop only determines by the transverse component of the magnetization, right? It's not this direction doesn't matter, but it's really this direction that matters. So in MRI, we can only observe two directions, just the transverse components of the magnetization. We cannot observe the entire magnetization directly. And we'll talk more about that. But effectively, we're getting some signal over here. Now, what is it similar to? It's similar to this apparatus. I have this, look, this is an apparatus that I made. This is a spinning top. It's a magnetic spinning top. And because it's rotating here, it's a rotating magnetic spinning top. Now I put it above a magnet such that it's actually now levitating in a stable position, semi-stable position. And I put a coil that is connected to a microphone. And I'm recording what this microphone is picking up. And you can see now that it's picking up this EMF that is induced inside this loop because this thing is rotating. So it's a very similar phenomenon. And now, if I would then go, thank you. If then I would go and compute, let's say, what is the frequency, you'll see that it's going to have some typical frequency, resonance frequency of this precession that this thing was going at. And it's, I don't know, 25 hertz or so. All right. Pretty awesome. Huh? Okay. So now, here's the situation. We said that the signal in MRI comes from protons, in the body, and it actually comes mostly from water. So hydrogen or protons in water. That's where it comes mostly from, because we're 70% water. Now, consider this glass of water that I put inside the magnet. I put inside the magnet, it's going to magnetize. So what's going to happen is that there's going to be a net magnetic moment generated in this glass of water, right? Now, what I'm going to do now is I'm going to perform some excitation somehow. I'm going to apply some radio frequency pulse. And that is going to excite this magnetization of the water. And in turn, what's going to happen is that the water are going to emit a radio frequency back. And that radio frequency that they're going to emit back, it's due to this precession that it's going to do. And that precession is at the frequency that is proportional to the magnetic field. So I'm going to receive a signal. The time signal is going to look something like this. It's going to have a particular frequency. And if I look at the spectrum, that spectrum is going to, it's just going to be proportional to this magnetic field. If I make the magnetic field stronger, then the frequency is just going to increase. Okay? The frequency that I'm going to pick up is going to increase. And yeah, so it's just going to be faster. Now, of course, it's going to decay, just do some relaxation properties, but obviously, it's going to produce a frequency around this point. Is that clear? Put water, spins inside a scanner, they magnetize, we somehow excite them using RF. That phenomenon is interesting, but we'll talk about it more. That tips the magnetization somehow, and now it starts processing and producing the signal, which is also called free induction decay or FID. And I pick this up. That's great. All right, so now I know, based on the frequency, I know what is the field that this water is actually observing. If I know gamma and I know the frequency, I can actually tell you what is the frequency, what is the field strength of that magnet that the water sees. Okay, but here's the deal. This is not an image, because let's say I put now 1, 2, 3 glasses of water, and each one, let's say, has a slightly different amount of water. And I perform the exact same excitation and I receive a signal. Because this field is uniform, all these water glasses see exactly the same field. And so the signal that they're going to emit is going to be at the same frequency. So I illustrated the colors corresponding to these, but the signal is of course, added together, right? And then if I compute the spectrum, I will still see a spectrum at exactly the same location. I am missing spatial information here. I cannot create an image. So what can I do in order to actually make an image? I want to be able to distinguish between these glasses of water. What can I do?
Use a gradient field. Change B naught across the distance.
That's a Nobel Prize. You know, Julian, if you came up with this idea in 1972 or so, you would get a Nobel Prize for it. Absolutely. What we do is we add an extra field. What kind of field? Well, it's a field. Oh, sorry, I had a better thing. Okay, before I do that, it's missing extra information. So what I can think of it is that I have a piano, and no matter where I'm going to hit this piano, is going to produce a single tone. So if I hit it here, I hit it here, I hit it here, it's just going to produce the same freaking sound because it just has one key. All right, that's a problematic piano. Does that make sense, this analogy? Like no matter where I put it on the piano, like where I press, it's going to produce exactly the same tone. That's my situation here. No matter where I put the glasses of water, they're going to produce exactly the same tone. So now Julian suggested, yeah, add another field. And that field still points in the same direction. It points in the same direction, but at the center, it's unchanged. So the field in the center is exactly the same. The field on the right is stronger, still pointing in the same direction, but it's stronger. And the field on the left is weaker. So it's still put in this direction, but it's just slightly weaker. So I don't know if you notice, it's pretty subtle, but now there's a subtle change in the frequency that, first of all, there's a change in the field that each one of those water glasses see. And so there is also a change in the frequency that they emit. And so what I can do now is I can look at this time signal. You see there is a slight change here. What I can do now is zoom in. I'm going to zoom in and just show you kind of how it looks like. This is the time signal. And of course, it's added together. It's not separated, but I'm just separating, showing this for just illustration purposes. And so what you'll see is that the signal from the yellow cup is going to be a little bit to the left, the spectrum. And the signal from this cup is going to have a slightly different spectrum and frequency, and this one will have a slightly different. But because this change is linear, so field maps linearly to space, there is a one-to-one correspondence between the position of those water glasses and also the frequencies that they emit. And in fact, if this is the time signal that I get from MRI, if I take a Fourier transform, I will get a picture, an image of those water glasses. This is actually the image of the water glasses. But in order to get that image, I have to take the signal that I capture in MRI and compute a Fourier transform of it in order to get the image. So in fact, MRI collects data in the frequency domain of the image, because each spin position corresponds to a frequency. And in order to decode it, I need to compute a Fourier transform. This is more like a full piano now, where you can think of spins as keys being pressed. And in a piano, the position of the key is linearly proportional to its frequency. So it's very similar. And of course, you can imagine now, if I told you to close your eyes just turn on a recorder, and now I'm going to play a few on a piano. You recorded that signal, and if you computed the spectrum, you tell me which keys I keyed, right? And that's very similar to the case of MRI, where if I record the signal coming from the spins and I compute the spectrum, I can tell you where they're from, if I have a gradient on. Does that make sense? Now, okay, this is all good in 1D.
Oh,
But what
Mickey, I
happens in
think,
2D? Yeah.
sorry, there's a question in the chat.
Yeah. Yeah, whether it's lower, yeah, Anita, you caught me here on a thing. Whether it's lower or higher, it's yeah, in that case, I guess should have been lower, but it's a little bit yeah, I guess you know, this is with respect to a reference, so this would be a negative high frequency, this would be a positive high frequency. It's a little bit subtlety here, but yeah, you're kind of right in some way. This I'm just showing you the real part here, so it's a little bit difficult, but definitely there's one-to-one correspondent between the spectrum. So if that's okay, but you caught me here on a little bit of a subtlety, Anita, as always. Thank you. So what? This was 1D, but how can you do it in 2D? How can you then resolve an image in 2D? I mean, obviously you can only put a gradient in one direction. If I add a gradient in a different direction, it will just rotate the gradient. It'd still be a gradient oriented in one direction. So how can I get an image? Well, what can I do is I can apply a gradient in X. And if I have spins oriented in space like this, it's very similar to pressing this key, and this key on a piano. That will produce then a certain spectrum, right? So I will capture a spectrum corresponding to that frequency, and this frequency, right? If I apply a gradient in the X direction. If I then go and apply a gradient now in the Y direction and collect a signal, well, then this spin and this spin, it's like will be the same as pressing this key very hard. And this spin here will be pressing this key. And the signal that I'm going to get is going to be a frequency corresponding to this tone and a frequency corresponding to this tone. And then I can apply X and Y gradient together, like here. And in this case, this spin will produce this tone, and these two spins will produce these tones. So now their frequency is going to change based on the gradients that I'm applying. So if I know that I have 3 spins and I acquired data with 3 gradients, I have 3 unknowns, I have 3 measurements, and I can actually solve where these spins are. 3 equations unknowns. If I have though a distribution, then I probably need a lot more measurements, right? But in order to solve 3, that's relatively easy. I just need 3 measurements. And so this is the first measurements. That's the spectrum that I'm going to get from that measurement. This is the second measurement. That's the spectrum I'm going to get. And this is the third measurement. This is the spectrum I'm going to get. And for these spectra, I can then go back and try to reconstruct where those spins were. So what I can do is I could do what's called a back projection, or try to figure out where they are. So I know that if I have this spectrum, then I should definitely have maybe something here, and something here. So I can kind of like mark the spaces where it's possible to have a spin. It could be somewhere here, I don't know where. It could be here, I don't know where, but like definitely along those lines. What about here? Well, I can also do exactly the same thing, so it could be either now along this part or along this part. But now there's just a few places that there overlap. So now I have this place, this place, this place, this place that I can suspect as being where the spins are. And now I can do exactly the same in this direction. And I'm going to look at the most likely 3 places, right, that has the most, overlap. And those likely 3 places are going to be here. So I can actually create an image. This is called back projection. It's actually very similar to CT. This is how you do CT. So very similar to MRI, but that's kind of the idea how you create. This is actually how Lauterberg described MRI in his first paper. And he called it actually MRI zygmatography. And I know why this term didn't actually catch up, because it's just too long. So it wasn't good at naming things. But this is exactly the idea. You put some tubes inside the scanner, and then you apply gradients, and then you see different spectra coming out. And then you can resolve an image based on this. And this is the first image ever of 2 tubes being created using MRI.
Question?
Using this phenomenon. Now, here's the deal. I had supposed to have some animation here. But anyway, I'm running out of time. If this is an image, what I'm showing you here is the magnitude of its 2-dimensional Fourier transform. Now, if I look at the projection of an image, actually, according to the center slice theorem, that Bracewell's center slice theorem, a projection is the same information of a line in the 2-dimensional Fourier transform. So it's in a similar way, if I did a projection of this entire image, it's the same thing as collecting one line in the 2-dimensional Fourier transform of the image. So in some ways, doing those gradients and rotating them and collecting data is very similar as collecting data in the multi-dimensional Fourier transform, 2-dimensional Fourier transform of that object along radial lines in the frequency domain. I'm not going to derive it for you right now. I'm just saying that applying a gradient in different orientations would give you information on the 2D Fourier transform. In an MRI, you can actually do that and get this type of information and reconstruct it in a similar way that you would construct computed tomography. But MRI is way more flexible. In fact, in MRI, you not only can collect data along radial lines, but you can also collect them along Cartesian lines. And you can also collect them along spiral trajectories. There's a lot of possibilities in order to do this. But it's pretty much traveling in the frequency domain of the image, collecting data while changing the gradients in order to sample different parts of the image. And the way it's done is, it kind of looks like this. This is collecting data. This is collecting data line by line in a 2-dimensional Fourier transform. And the more lines that I collect and I take a Fourier transform, then I would create something that looks more like an image. Okay. But the idea here is somehow there's this Fourier domain that I collect the data, and I need a Fourier transform in order to reconstruct it. Okay, that's a key thing that you need to understand. All right. Okay, I'm going to, I think, finish here. The idea, again, that I wanted to give you is this key points, which are the fact that there is a frequency correspond to the frequency that the spins emit correspond to the field that they see. And we map field to position using gradient fields. And therefore, by receiving the signal, after you apply a gradient field, you can then decode the position of the spins. Somehow it ends up being, could be a 1-dimensional Fourier transform, but actually it ends up being a multi-dimensional Fourier transform of the image somehow. We'll talk more about why is that the case later. But once you understand that in MRI, you sample in the Fourier transform of the image, everything becomes more clear because you know how much you need to sample, you know how far you need to sample, you know how closely you need to sample in order to create an image. And we'll talk more about that next time. I'm running a little bit late in terms of the material, but don't worry, I'm gonna go slow, so maybe it will sync better for you. All right. So next time what I'm going to do is I'm going to little bit elaborate on what I've covered so far. I'm going to teach you a little bit about excitation and how to actually selectively excite certain parts. We're going to talk a little bit more about contrast, of how contrast is generated. And then I'm going to move into kind of background material, talking about 2D Fourier transforms in general, and a little about signal processing, such that we develop this language between us so we can then go, and when we do the full analysis of MRI, we have the same language. Okay, so hopefully you'll have a nice weekend. I mean, we did assign a homework. You can go and start at it. Feel free to start at it. It's all prerequisite material, that some of it we're gonna cover and some of it not. But I'd like you to go and attempt to solve, because it will require you to go through some derivation of two-dimensional Fourier transform, what happens, the derivative property, the shift property of the Fourier transform, and so on and so forth. Okay, so with that, thank you very much for sticking up, and yeah, I'll see you all next week.